Hello everyone, and thanks for watching Edupedia World Videos. This video introduces a new topic called Gauss Law. Now, earlier we've learned the first important law in electrostatics, and that is Coulomb's law. And it tells us that the force between two charged particles, or rather the magnitude of the force, is equal to k q1 q2 by r square, and of course like charges repel and unlike charges attract. Now there's another law called Gauss law, which does pretty much the same thing. It tells us the force between two charges, but in a slightly different manner. From the force being k q1 q2 by r square, we were able to deduce that the electric field due to a single point charge will be k q by r square, right? And from the electric field we could calculate electric potential and other quantities of interest. Gauss law, instead of telling us the force directly, tells us the electric field directly. And from the electric field created by a configuration of charges, you can then multiply by the second charge to get the force between the first charge configuration and the second charge. So Gauss law and Coulomb's law are pretty much equivalent. In fact, Gauss law can be derived from Coulomb's law and Coulomb's law can be derived from Gauss law. There are just certain specific situations in which Gauss law is much more useful and problems can be solved much more easily. So we'll begin by learning a few concepts which are important in understanding Gauss law, and then we'll try to derive Gauss law from Coulomb's law. The first concept is that of electric flux. Electric flux is qualitatively a measure of how much electric field flows through a particular area. So if we have a small area, let's say the magnitude of the area is delta S, the direction of the area vector, remember, it is always perpendicular to the area. So if this is the area, the small area in the horizontal direction, you can imagine it lying on a horizontal table, then in the vertically upward direction or in the vertically downward direction, that's up to us, we can choose either one of the two, will be the area vector, right? So if there's a small area of magnitude delta S and there's an electric field E flowing through the region, then the electric flux through this particular area delta phi, a small amount of electric flux, is equal to E dot delta S. If this angle is theta, this is the direction of delta S, so this can also be written as E delta S cos theta, right? So this is the definition of electric flux, of a small amount of electric flux. That is, to calculate the flux over a big region, for example, if you have a sphere and you wanted to calculate the flux over the northern hemispherical surface, then you could calculate the electric flux due through individual areas, small element areas, and you could integrate it to get the electric flux through the total area. Electric flux, you can see from this definition, is a scalar. It is the dot product of two vectors. What are those two vectors? The first vector is the electric field, and the second vector is what is called the area vector. The area vector has a magnitude equal to the area of the surface, delta S in this case, and the area vector has a direction that is perpendicular to the area, to the surface. So, and the angle between them is theta, and A dot B is mod A mod B cos theta, so delta phi is E delta S cos theta. If we wanted to calculate the total flux through an area, that would be integral of E dot ds. Right, now we'll take a differential area and we'll integrate through the whole area. This would be the total electric flux. Now remember, we saw in the last videos that electricity and gravitation have a lot in common simply by virtue of the fact that Coulomb's law and Newton's gravitational law have the similar structure, gm1 m2 by r squared and k q1 q2 by r squared. So if the Coulomb's law has an analogous Gauss law, then gravitational force or Newton's gravitational law should also have an analogous law, and there actually does exist. It's generally not that useful and is not really applied a lot, but mathematically it does exist. Everything we'll do for electricity now, as long as we follow it from Coulomb's law, will be valid for gravitation as well. In particular, there is also something called the gravitational flux, which, you guessed it, is equal to the integral of the gravitational field dot ds. Right. Now, sometimes we'll actually calculate the flux through a complete area, a closed area. It might be a spherical area, it might be a cube, three-dimensional cube, right? But if we wanted to calculate the flux through a closed surface, then the sign we use in the integral is we put a circle over it to denote that this integral is over a closed surface. For example, if you wanted to calculate the electric flux flowed through the room in which you are sitting in right now, that room will probably be cuboidal in shape, and that room is a closed surface. If you calculate the flux through each wall and add it up, that will give you the total flux. For the flux through each wall, you'll have to calculate the flux through individual areas and add them up. Right. So this is the first quantity of interest, electric flux. The second quantity of interest in understanding Gauss law is something we've already seen before in, I think, the very first video or the second video, and that is the concept of solid angle. I'll briefly revise it here again because it is very important when it comes to Gauss law. So the definition of a plane angle is, if you take two lines that are intersecting, then if you take the intersection as the center and draw a circular arc of any radius whatsoever, it doesn't matter, and calculate the length of this curve, then this angle theta is defined as L by R. Now the radius doesn't matter, because if you took half the radius, this length would be half as well. If you took 3 times the radius, then the length of this curve would be 3 times as well. So theta would still be the same. This is the definition of a plane angle. Similarly, the analogous view of two lines intersecting would be actually having a cone intersect, a three-dimensional cone. And for that, instead of plane angle, we have something called a solid angle. And it is defined in a similar way. We take this intersection or this vertex in this case as the center, and we construct a sphere of any radius whatsoever. Here it was a circle, this is a two-dimensional figure. Here it's a sphere, this is a three-dimensional figure. And in this case, the solid angle is defined as the area of this section of the sphere divided by r squared. Now area has a dimension of r squared and r squared has the same dimension. So solid angle, just like plane angle, is a dimensionless quantity. Right. Now if we take a complete sphere, then the surface area is 4 pi r squared. If we divide it by r squared, we get 4 pi. That means a sphere, a complete sphere, subtends a solid angle of 4 pi at the center. Just like a circle subtends an angle of 2 pi at the center. A circle subtends an angle of 360 degrees, and that is 2 pi radians. In this case, the unit is STR or steradians. This is all stuff that we've seen before in the very first videos of units and dimensions. So, two important things here. One, the definition of solid angle, and the other, the fact that if we take a completely closed surface, then it subtends an angle of 4 pi steradians any point inside the surface. The angle subtended any point outside the surface is 0. Just like if you take a circle and if you complete the circle, then this angle will keep on decreasing and ultimately it will be 0. So a circle subtends an angle of 2 pi at any point inside the circle, and it subtends an angle of 0 at any point outside the circle. Similarly, a sphere, or rather any completely closed surface, it could be a surface like this as well, subtends a total angle of 4 pi, a total solid angle of 4 pi at any point inside it, and a total solid angle of 0 at any point outside it. Now, if this A is the area that is perpendicular to this radius, then this is the A we'll use. But sometimes we'll actually know an area that is at an angle. Let me draw another figure to make it clearer to you. So let's say this is omega, and let's say this area is A and this is R. Then omega will be equal to A by R square. But let's say this area is not an area we know. We actually happen to know a tilted area. We know this area. And let's call this area A for a second, such that this new area vector makes an angle of alpha with the original area vector. So in that case, we'll have to take the projection of this area along the original area, and that will be this perpendicular area, which would be smaller than the original value, and its value will be equal to A cos alpha. So in this case, the solid angle is A cos alpha by R square. If alpha is 0, that means this tilted area, we actually tilt it further and it becomes parallel to this perpendicular area. Then omega will become A by R square, because that was the original definition. We see that if we tilt this particular area, then the area of this particular surface increases, but the solid angle remains the same. So to compensate for that, we'll have to take the projection perpendicular to it. So this is the general formula for solid angle subtended by a surface at a particular point. Let's move on to Gauss law now. First I'll write the complete statement of Gauss law, and then we'll focus on the individual parts because the details matter in this a lot. So Gauss law states that the total flux of the net electric field is a keyword here. I'll focus on this again soon. Flux of the net electric field through a closed surface equals the charge enclosed by the surface divided by epsilon naught. Or if I were to write it mathematically, the total flux is equal to Q in by epsilon naught. Now let's look at this equation a little bit deeper. One of the important terms here is the net electric field. And what does that mean? So let's say we have 5 charges, 1, 2, 3, 4 and 5. And we are considering this particular closed surface. It's a 3-dimensional closed surface. So the Gauss law says that the flux of net electric field through this surface, let's call this surface S, the flux of net electric field through this surface is equal to the charge enclosed by the surface divided by epsilon naught. So the net electric field means the electric field due to all the charges. That means the flux due to the electric field of 1 plus 2 plus 3 plus 4 plus 5. The net electric field at this point dot ds will be the flux through this small area, flux through this area, flux through this area, flux through this area. You add the total flux of the net electric field, but that will not give you the net charge by epsilon naught. It will give you the charge enclosed by epsilon naught. What is the charge enclosed within this surface? 1 plus 4 plus 5. Right? 2 and 3 are not enclosed. So this is an important point where sometimes students make errors. In the LHS, you have to take 1, 2, 3, 4 and 5. You have to take the electric field due to all the charges present in the universe. So any surface you take, the electric field, the flux of the electric field through that surface has to include the electric field due to every possible charge imaginable. But in the RHS, we don't have the total charge divided by epsilon naught. We only have the charge enclosed by the surface, the charge inside this surface divided by epsilon naught. So that will be 1, 4 and 5. Now what if we were to add some other charges? We were to add 6, 7, 8, 9 here. The right hand side would still remain the same because none of these charges are inside this surface. Inside this surface, let's say this has a magnitude of 5 Coulomb, this has a magnitude of 5 Coulomb, but this has a magnitude of 2 Coulomb. Then the total charge inside this closed surface is still 12 Coulomb. Epsilon naught is a constant. So no matter how many charges you add outside, the RHS will remain the same. That means by Gauss law, the LHS will remain the same. Does that mean the electric field at this point will remain the same? No. The electric field at every point will change with the addition of new charges because their electric field would add to the original electric field. So even though the electric field will change when I add another 10th charge here, the electric field will change in such a way that the flux through this surface will remain the same. So the total flux through this surface of the electric field of all the charges actually depends only on the charges inside this. So now we've introduced a lot of new things. So let's go back to the basics and try to derive Gauss law from Coulomb's law. So the one important principle we'll use here is the principle of superposition, which says that the force between any two charges is completely independent of the force of the presence of any other charges. You take the interaction between any two and you add them up, right? So let's say we have a single charge here, Q, and let's say we take a random surface around Q. This is not a spherical surface, this is a completely random surface, right? And we'll take a small area here, delta S, and we know the electric field here will be radially outward. What is the small flux through this area? That will be equal to E into delta S into cos alpha, where if this is perpendicular to the area and this is the direction of E, then the alpha will be the angle between them, right? In this case, it's actually, I made the figure which looks a little bit spherical, so you can't really see the difference. But if you want to imagine it, imagine this is Q and this is sort of this surface which you have. In that case, this will be delta S perpendicular to the area, but the direction of electric field will be this, so there will be an angle, right? So delta phi is E delta S cos alpha. I can write it as KQ by R square delta S cos alpha, right? Because the electric field at a distance r, now this r changes with delta S. If delta S is here or here or here, r is different because this is not a sphere, this is a random surface. But if r at this point the distance is r, then KQ by R square will be the electric field radially outwards. So this will be the small amount of flux. We can write this as KQ times delta S cos alpha by R square, right? Now what is delta S cos alpha by R square? If this angle is alpha and this is the radially outward direction, then delta S cos alpha is the area perpendicular to the electric field, the projection of area perpendicular to the electric field. You divide that by R square, what will you get? You will get the solid angle subtended by this small radius, right? So delta phi comes out to be KQ times delta omega. Delta omega is the solid angle subtended by this small area. If you take a small area over here, then it will subtend a delta omega here, and delta S cos alpha by R square, where R will be this particular value, will give me that delta omega. Now you can just integrate. So this should be small q, sorry. And delta phi will give me the total flux, that will be equal to KQ, which are both constants, times the integral of delta omega. Now delta omega is the solid angle. If you integrate the solid angle, you'll get the total solid angle subtended by a closed surface at a point in its interior, which is equal to 4 pi. Now remember, we had two separate constants, k and epsilon naught, which were related by k is equal to 1 by 4 pi epsilon naught. So if you substitute that value here, 1 by 4 pi epsilon naught, you will get phi is equal to q by epsilon naught, right? I'll repeat this once more because this is important. The small flux through any area delta S will be E times delta S times cos alpha. E is equal to KQ by R square. You take R square towards the right, you get KQ, which is a constant, times delta cos alpha by R square, which as it turns out is equal to the solid angle subtended. You add up all the solid angles subtended, you'll get a total of 4 pi, because that is the solid angle subtended by any closed surface at a point in its interior. Just like if you take any closed two-dimensional loop and you add all the angles subtended, they will end up giving you 360 degrees, because that is the total angle inside the loop. So this gives me phi is, the flux is q by epsilon naught. Now this is just one part of the law. So right now we know if I have a single charge q, and if I take a loop that in which q is in the interior of this loop, then the flux through this loop will be q by epsilon naught. It doesn't depend on the radius at all. right? And in fact, this loop doesn't even need to be spherical. It can be any loop like this. The flux through all of these loops, closed loops, is the same q by epsilon naught. Now what if I add another loop? If this was q1, what if I add another charge q2? Right, the flux because of that would be q2 by epsilon naught. Now if you add the flux due to both of them, it will be q1 plus q2 by epsilon naught. So we see, due to the superposition principle, the total charge enclosed will be q1 plus q2 plus q3 plus whatever charges are there, and the total flux will be that divided by epsilon naught. What about outside charges, however? So let's say we have this surface. What if the charge was outside the surface? In that case, when we were integrating delta omega, instead of getting 4 pi, we would get 0. Because this closed surface subtends an angle of 4 pi at any point in its interior, but it subtends an angle of 0 at any point in its exterior. Right? So even though the flux is calculated using the electric field of this point as well, the flux actually ends up being 0. Another way to look at it is, all the electric field lines that go inside come outside as well. There is no electric field lines produced inside this surface. So the flux, electric flux, due to the electric field of this charge around this surface is 0. Right? So that tells us that if there are 5 charges and you take this particular loop, the flux of electric field through this loop of this and this and this would give you this q by epsilon naught, this q by epsilon naught, this q by epsilon naught. The flux of electric field due to these two charges would be 0, even though the electric fields themselves would not be 0. Right? So you add other charges here, the electric field at these points will change, but they will change in such a way that the flux through this particular loop will stay the same, because any point outside this will actually have an electric flux of 0 through this loop, because the integral of delta omega will be 0. Right. So now we've seen Gauss law. I'll just write it once more. Flux is equal to, now we've used a closed integral sign because we're taking it over a closed surface, E dot ds is equal to q in by epsilon naught. This is Gauss law. In the next video, we'll see many different applications of Gauss law and see how problems are greatly simplified by using this method.